Now that we've talked a bit about orbits, I want to mention another orbit that's interesting for an object circling the Earth. It's called a geosynchronous orbit. And why is this orbit important? Basically, if you can get an object to go around the Earth, and it would have to go around the Earth's equator, every 24 hours, it'll actually stay above the same point of the Earth all the time. Think about that. The Earth's turning every 24 hours, and the object's turning around the Earth every 24 hours. So it's remaining above the same point of the Earth. Now you can think of perhaps several reasons why this would be useful. One would be if you're trying to spy on somebody or something at a certain point on the Earth. That's one way to do it. Another very different application would be something like radio repeaters or television satellites or something like that, where you want to be able to point your antenna to a certain direction and always know that you'll have a satellite there that you can get a signal from. Given their importance, I thought it would be useful to consider what would be the height above the Earth that would result in a geosynchronous orbit. You can use the same approach we used earlier for the orbit of the Moon, which is 27.3 days, which is going to be much higher than a geosynchronous orbit. Using a geosynchronous orbit, it would take 24 hours, so you'd have to convert that to seconds and determine what the associated height above the Earth would be for that geosynchronous orbit, solving the equation for r. So I encourage you to try that. I'll do it separately because it's very difficult, as I mentioned, to write things on PowerPoint. It's one of the shortcomings of PowerPoint unless you have some sort of a tablet. And let's see if there's something else I want to say. Yeah. The other thing you could do is you could find a planet. You can look all of this up on the internet. You can find Mars, Pluto. I guess Pluto isn't really a planet anymore. It's a minor planet. But anything, any object circling the sun, you can find out how far it is away from the sun. And from that, you can determine how long it's going to take to go around the sun. And you can calculate it and then check your work with information you can find online. So all of a sudden, you have 9 different objects you can practice this orbits problem on. Picking the sun as the central orbiting object, you'd have to find the mass of the sun, of course. Then you'd have to know the distance from the sun to any one of the planets, and the period for the planet to go around the sun. So this is a nice exercise that I encourage you to do. I'll do one exercise separately on a piece of paper to show you one of these problems so that you could then approach it as well. Now in the homework problem, I think it asks for a geosynchronous orbit, or I can't remember if it's geosynchronous or Earth to Moon. But on one of them, it wants to know the distance from the surface of the Earth to the orbiting body. Think about how you'd find that. If you knew the distance between the center of the Earth and the orbiting body, the distance between the surface of the Earth and the orbiting body should be similar to that number, but you have the radius of the Earth that you have to take into account. So hopefully you'll be able to see that as you do the homework problems. Okay, this video was shorter, and hopefully it'll give you what you need to know to work on the homework problems. And I'll see you next Monday. The lab will be on, I think it's the Marshmallow Lab. I think it's the Marshmallow Lab next Monday, unless you did that one already. I can't remember. Anyway, I'll send an update on that later. And I'll also send an update on what the quiz is going to be on Monday as well. Okay, take care. Bye-bye.